Good morning, students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. And we have a subject, probabilistic modeling and reasoning, as a part of curriculum of third semester Artificial Intelligence and Machine Learning course. So, in that course, we are discussing the concepts of Module 1 titled Principal Component Analysis. And in the last lecture, we are being introduced with QR factorization. Means what is QR factorization of a given matrix. Now we are going to see the QR factorization example, how to reduce the factors Q and R for a given matrix by using Gram-Schmidt process. Okay, let us look into the concept in detail. So first let us have a recap over the concept of QR factorization. Any given non-zero matrix A can be written as the product of two matrices. Any given matrix A can be written as the product of two matrices, or we can say A can be decomposed into the product of two matrices. The first matrix is called as Q and the second matrix is named as R, and the Q behaves in such a way that Q is orthogonal. Q is orthogonal. And R has a specific behavior that R is an upper triangular matrix. So always we can decompose a given matrix A into a product of an orthogonal matrix and an upper triangular matrix. Orthogonal matrix, you know that Q transpose into Q is equal to I, and hence Q is called orthogonal. So we call a matrix Q as orthogonal if the product of its transpose and itself is identity matrix. That means every vector in Q, every column vector in Q is orthogonal to, every column vector in Q is orthogonal to the other vector in Q. That means every pair of vectors in Q behaves orthogonally. And also this Q is normal, orthonormal also. Orthonormal means if you write Q as Q1, Q2, Q3, that is a 3 by 3 matrix which is having three columns Q1, Q2, Q3. Orthogonality means Q1 dot Q2 is 0, Q2 dot Q3 is 0, and Q1 dot Q3 is 0. That means the dot product of every pair of vectors is 0. That leads to orthogonality. And normality means norm of Q1 is 1 and the norm of Q2 is 1 and the norm of Q3 is 1. That means each vector Q1, Q2, Q3 are of unit size, unit vectors. So we are going to decompose the matrix A into product of two matrices such that first matrix is orthogonal and second matrix upper triangle. Okay, this is called QR decomposition. Now this is just an outline picture of A when it is decomposed into QR. This represents our matrix Q, this represents our matrix R. And here Q is orthogonal and clearly R is upper triangle. You can see that the diagonal elements will be non-zeros. Definitely the diagonal elements will be non-zeros, and the elements which are lying above the diagonal are also non-zeros, and the elements which are lying below the diagonals will be zeros. Okay, this is the behavior of an upper triangle matrix, especially the R diagonal elements and the elements lying above the diagonal elements are non-zeros. And normality, each column vector of Q is of unit size, and every pair of vectors in Q results into 0. The product of every pair of vectors in Q results into 0. That is called orthogonal. So orthogonal and normal both mixed as orthonormal. Okay. So this is about briefly the meaning of QR decomposition of a matrix. Now, let us take an example. Let us take an example, the matrix A, capital A, which is having three columns A1, A2, A3, namely A1, A2, A3, and four rows 1, 2, 3, 4. So, obviously, the matrix A is of order 4 rows and 3 columns. 4 rows and 3 columns. Now, we are going to decompose this A into product of two matrices, where the first matrix is denoted by Q, which contains three columns Q1, Q2, Q3. Why three columns? Because the original matrix contains three columns. Definitely, the number of columns in Q will be equal to the number of columns in A. That is why Q1, Q2, Q3. And R will be like, because this will be again a 4 by 3, and this will be a 3 by 3 matrix, and it is an upper triangle matrix. This is what we are going to observe. Let us see how the mathematical work goes on, how the mathematical steps will be taking place. The process is suggested by Graham Schmidt, and hence this is called Graham-Schmidt process of QR decomposition. Okay, so we are going to decompose a matrix by using Graham-Schmidt process. Now, let us consider the first column vector, of given matrix A, that is A1. This is our given matrix, first column vector, minus 1, 1, minus 1, 1. Now, we are calculating the norm of A1. Norm of A1. You know, the norm of a vector ABCD. What can you say about the norm of the vector ABCD? Simple. The norm of the vector ABCD is nothing but root of A square plus B square plus C square plus D square. This is a well-known formula from our elementary vector algebra. So, for a vector ABCD, we can calculate norm as root of sum of squares of the elements. In the same way, if you calculate the norm of this vector, it will be root of minus 1 whole square plus 1 square plus minus 1 whole square plus 1 square. And hence, we get root 4. And hence, the answer is 2. So, the norm of this vector is 2. Now, I am going to define a vector q1. I am going to define a vector q1 as the vector a1 multiplied with its norm. That means q1 is nothing but a1 by norm a1. The vector a1, which is where every component is multiplied or divided by norm a1. So with this formula, if we calculate q1, what happens? Let us see. So this is our a1. We are dividing it with norm a1. Okay. What is norm a1? Norm a1 is 2. So we have to divide every element with 2. So what happens? Minus 1 by 2. Minus 1 by 2. 1 by 2. Minus 1 by 2. And 1 by 2. Okay. So let me write more clear. When we take a1 minus 1, 1, minus 1, 1, then norm a1 will be root of minus 1 whole square plus 1 square plus minus 1 whole square plus 1 square, and hence it is root 4, hence 2. Now, we are defining q1 as a1 by norm a1. That means 1 by 2 times of minus 1, 1, minus 1, 1. Then automatically it results into minus 1 by 2, 1 by 2, and minus 1 by 2 and 1 by 2. So this is the way how we will obtain the first column of our vector q. You know, we are mentioning q as q1, q2, q3. So here we have obtained q1. And we name this norm a1 as R11. Norm a11 as R1. So we have calculated two things here. One is Q1 and another one is R11. Okay. With this, we will proceed to the next step of the process, next part of the process. When we move to the next process, we are going to calculate, in this part, we are going to calculate Q2 bar, okay, and hence we'll calculate Q2. And during this process, we also calculate R12 as well as R2. So, in the part 2, we are going to calculate four important components, namely Q2 or three components Q2, R12, R2. Q2 is for the matrix Q and R12, R22 are for the matrix R. Okay, let us see how we are going to calculate. For your better understanding, I'll always write here what is Q. Q is Q1, Q2, Q3, where Q1 is already calculated. Now we are going to calculate Q2. And R is an upper triangle matrix, okay, with R11, R12, R13, 0, R22, R23, 0, 0, R3. In the previous part, we have calculated R11. Now we are going to calculate R12 and R22, R12 and R2. Okay, here. Let us see how we are going to do. R12 is calculated with the help of the formula according to Gram-Schmidt. R12 will be calculated with the help of the formula Q1 transpose dot A2. Q1 transpose dot A2. Let us take what is Q1. Q1 is nothing but just now we have obtained minus 1 by 2, 1 by 2, minus 1 by 2, 1 by 2. This is our Q1. And dot product with A1. A1 is, A2. Dot product with A2, which is minus 1, 3, minus 1, 3. Dot product with A2, which is minus 1, 3, minus 1. You can observe that the dot product will result into 1 by 2 plus 3 by 2 plus 1 by 2 plus 3 by 2. And hence, you will get 1 by 2 plus 1 by 2, 1, and 3 by 2 plus 3 by 2, that is 6 by 2, that is 3, and hence 4. So R12 is 4. Okay. Now we are going to calculate the modified Q2, or we are going to calculate Q2 bar. Q2 bar, you can simply say Q2 bar with the help of formula A2 minus R12 into Q1. A2 is nothing but minus 1, 3, minus 1, 3, minus R12. R12 just now we found that 4. R12 just now we found that 4, so it is 4. Q1 in the previous part we have calculated it as minus 1 by 2 and 1 by 2, minus 1 by 2 and 1 by 2. So when you subtract the corresponding elements, you will get the answer 1, 1, 1, 1. The answer is 1, 1, 1, 1. So this is our Q2 bar. Now let us take the norm of Q2 bar. Norm of Q2 bar, which we denote as R2. Of course, we can name it as R2. So this is root of 1 square plus 1 square plus 1 square plus 1 square, which is nothing but 2. When we get R22, now finally our goal is to calculate Q2. Q2 will be now Q2 bar divided by norm Q2 bar. Q2 bar divided by norm Q2 bar. So Q2 bar is nothing but all ones, 1, 1, 1, 1. And norm Q2 bar is 2. So it is 1 by 2. So obviously we'll get 1 by 2, 1 by 2, 1 by 2, 1 by 2. So this is the way we have completed the second part of calculation. In the second part, we have calculated the vector Q2 and two numbers of upper triangle matrix R, that is R12 and R22. Okay. Now let us move to the final part or third. Yes, here we see the third part. As with the same motivation as we have done in the second part, R13 will be calculated. R13 will be calculated with the help of Q1 transpose dot A3. What is Q1 transpose? Q1 transpose is nothing but minus 1 by 2, 1 by 2, minus 1 by 2, 1 by 2. Dot Q A3. A3 is 1357. 1357. When you apply the dot product, you will get the answer 2. This is 2. And we calculate R23 with the help of formula Q2 transpose dot A3. Q2 transpose dot A3. And what is Q2? 1 by 2, 1 by 2, 1 by 2, 1 by 2 dot 1357. And this results into H. So we have successfully found R13 and R23. Okay. Now we will calculate Q3 bar with the help of formula A3 minus R13 Q1 minus R23 Q2. Of course, these formula are part and parcel of the Gram-Schmidt process. So we are refining A3 into Q3 bar now. How? We are subtracting two vectors from A3, where the first vector is R13Q1 and second vector is R23Q2. Let us substitute A3 and R13Q1, R23Q2 respective values like this. A3, R13Q1, R23Q2. Then we'll get Q3 bar as minus 2, minus 2, 2. So our Q3 bar as minus 2, minus 2, 2. Okay. Now finally, we'll calculate R33 by normalizing it. That is norm of Q3 bar. Norm of Q3 bar. That is root of minus 2 whole square minus 2 whole square 2 square plus 2 square. That is equal to 4. And automatically Q3 becomes 1 by norm Q3 bar into Q3 bar. And hence we get this vector. So we have successfully found in the part 1. So we have successfully found in the part 1 R11 and Q1. And in part 2 we have calculated R12 and R22 and Q2. And in part 3 we have calculated R13, R23, okay, and R33 and Q3. So this is the way we have obtained all the required things. Okay, let us summarize. So when we summarize the Gram-Schmidt process, of QR decomposition, it contains 3 parts for a 3 by 4 or 4 by 3 or 3 by 3 matrix. Part 1 will calculate R11 and Q1. In part 2 we'll calculate R12, R22, Q2. In part 3 we calculate R31, R32, R33 along with Q3. So we have Q1, Q2, Q3, and hence we can write the matrix Q, and we have R11, R12, R22, R31, R32, R33, and hence we can write the upper triangle matrix R. Let us see that. So here as we have calculated Q1, Q2, Q3 and substituting the respective columns, here we get the matrix Q. And as we have calculated R11, R12, R13, R22, R23, R33. So by substituting those numbers in the respective places, we have obtained R. And you can easily verify that the product of this matrix and this matrix is equal to the original matrix. And hence A is equal to QR. And you can verify the product of these two is 0, the dot product, and the product of these two is 0, and the product of these two is 0. Every pair of vectors is 0 and each vector is of norm 1, and hence this is orthonormal vectors. And clearly you see that the diagonals are non-zeros and the elements which are lying above the diagonals are non-zeros, and hence this is upper triangular matrix. So with this we can conclude that A is decomposed into two matrices Q into R, where Q is orthonormal and R is upper triangular. Okay, you can verify the product. Minus 1 by 2 into 1 by 2, 0, 1 by 2 into 1 by 2, 1 by 4. Like that, when we multiply A1 A2 plus B1 B2 plus C1 C2 plus C1 D2, you'll observe that the product is 0. Similarly, this dot product is also 0 and this dot product. That means every pair is acting orthogonal to each other. Okay, this is how we'll deduce the QR decomposition from the given matrix A by using the Gram-Schmidt process. So let us conclude this class with the geometrical interpretation of Q and R. Okay, suppose here we are taking a matrix 3, 4, 7, 5, which is a 2 by 2 matrix with 2 columns and 2 rows. And luckily, by using the same process of Gram-Schmidt, we have decomposed A into product of Q and R, where Q is the matrix minus 0.6 minus 0.8 minus 0.8 to 0.6, and R will be disclosed in the next slide while projecting that. Now let us confine it. Okay, so A is decomposed into Q into R, where Q is this. Now let us plot the original vectors, that is A1, A1, A2 on xy plane, as well as the resultant Q vector, that is Q1, Q2 on the same xy plane, and let us check how they are behaving. See here, sorry, this is 4, this is 7, 3, 4, 7. Okay. Now let us consider the first vector 3, 4. 3, 4 means 1, 2, 3. So this is 3, this is 4. So the vector will be this red line. This red line will be the A1 vector. Okay, this is our A1. This is our A1. And next vector 7, 5, that is A2. That means 7 is here, 5 is here. So this blue vector is our A2. This blue vector is our A2. Okay. So A1, A2. You can check that the angle is not 90 degrees here. The angle is some other acute angle, actually less than 90 degrees. Now let us take the Q1, Q2. The vector Q1, Q2 minus 0.6 minus 0.8. The vector will be minus 0.6 and minus 0.8 will be here. This yellow line denotes Q1. And minus 0.8, 0.6 is denoted by this small light blue line. This is our Q2. Now clearly you can observe that the angle is 90 degrees. So what we have seen, the original vectors are not perpendicular to each other, but the resultant Q1, Q2 are 90 perpendicular to each other with 90 degrees. And also the size of the vector is exactly 1 because it is normalized. So unit size, unit vectors. This is also unit vector. So that is why in Q, the vectors are perpendicular, that is orthogonality, and each vector is of unit size, that is normality, orthonormal vectors. Okay. Now let us see the behavior of R, matrix R. The matrix R is this. Of course, the A1 is the previous vector as it is, and A2 is as it is. But let us project R. R is first vector minus 5 and 0. Minus 5 and 0. Okay. Minus 5 and 0. This is minus 5 and 0. And second vector minus 8.2 and minus 2.6. Minus 8.2. Minus 8.2 will be here. And minus 2 points. Here some little mistake happened. So you can see that this is our R1 and this is our R2. R1 and R2. Okay, R1 and R2. And you have to understand that definitely one of these vectors will lie along y-axis. That is for sure. That is the upper triangularity. Upper triangularity means at least one vector will be along y-axis. That is what upper triangularity means. So both are fulfilled, and hence this is called orthogonal decomposition of vectors. Okay. With this, I'd like to conclude the class. In the next class, we'll discuss how to find pseudo inverse with the help of QR decomposition. Thanks for your patience listening. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.